Nonparametric density estimation. As usual in density estimation, assume that the sample x is equal to the set x to the t, where t is starting from 1 to n, is drawn independently from some unknown probability density, p dot. P hat dot is our estimator of p dot. We start with the univariate cases where x to the t are scalars and later generalized to the multidimensional case. The nonparametric estimator for the cumulative distribution function CDF f of x at point x is the proportion of sample points that are less than or equal to x. That is, f hat of x is equal to the number of the conditions of the set that x to the t, which is less than or equals to x, divided by n, where the number of the set x to the t, which is less than or equals to x, denotes the number of training instances, whose x to the t is less than or equal to 0, equals to x. Similarly, the nonparametric estimate for the density function can be calculated as p hat of x is equals to 1 over h times the number of x to the t, which is less than or equals to x plus h, minus the number of x to the t, which is less than or equals to x, then divided by n. H is the length of the interval, and the instances x to the t that fall in this interval are assumed to be close enough. The techniques given in this chapter are variants where different heuristics are used to determine the instances that are close and their effects on the estimate. Histogram estimator. The oldest and most popular method is the histogram, where the input space is divided into equal-sized intervals, named bins, given an origin x0 and a bin width h. The bins are the intervals. The half-open, half-closed interval between the left-hand side x0 plus m times h and the right-hand side x0 plus m plus 1 times h for positive and negative integers m, and the estimate is given as p hat of x is equals to the number of the set x to the t in the same bin as x divided by n times h. In constructing the histogram, we have to choose both an origin and a bin width. The choice of origin affects the estimate near boundaries of bins, but it is mainly the bin width that has an effect on the estimate. With small bins, the estimate is spiky, and with larger bins, the estimate is smoother. See figure 8.1. The estimate is 0 if no instance falls in a bin and there are discontinuities at bin boundaries. Still, one advantage of the histogram is that once the bin estimates are calculated and stored, we do not need to retain the training set. Figure 8.1 histograms for various bin lengths. X denote data points. The naive estimator, Silverman 1986, frees us from setting an origin. It is defined as p hat of x is equals to the number of x to the t which is greater than x minus h over 2 and which is less than or equals to x plus h over 2 divided by n times h, and is equal to the histogram estimate where x is always at the center of a bin of size h, see figure 8.2. The estimator can also be written as p hat of x is equals to 1 over n times h times the sigma summing with t starting from 1 to n of the term w times x minus x to the t then divided by h. So with the weight function defined as that w function, w of u is equals to 1 if the absolute value of u is less than 1/2 and is equals to 0 otherwise. This is as if each x to the t has a symmetric region of influence of size h around it and it contributes 1 for an x falling in its region. Then the nonparametric estimate is just the sum of influences of x to the t whose regions include x. Because this region of influence is hard 0 or 1, the estimate is not a continuous function and has jumps at x to the t plus minus h over 2. Kernel estimator to get a smooth estimate. We use a smooth weight function called a kernel function. The most popular is Gaussian kernel. K of u is equals to 1 over the square root of 2 pi times the exponential of to the minus u squared over 2. The kernel estimator, also called the Parsons windows, is defined as p hat of x is equals to 1 over n times h times the summations, summing with index t starting from 1 to n, of the function k of x minus x to the t divided by h. The kernel function k dot determines the shape of the influences, and the window width h determines the widths. Just like the naive estimate is the sum of boxes, the kernel estimate is the sum of bumps. Will the x to the t have an effect on the estimate at x, and this effect decreases smoothly as the absolute values of x minus x to the t increases. To simplify calculation, k dot can be taken to be 0 if the absolute values of x minus x to the t is greater than 3 times h. There exist other kernels easier to compute that can be used as long as k of u is maximum for u equals to 0 and decreasing symmetrically as the absolute values of u increases. So figure 8.3 is the kernel estimate for various bin lengths. When h is small, each training instance has a large effect in a small region and no effect on distant points. When h is larger, there is more overlap of the kernels and we get a smoother estimate. See figure 8.3. If k dot is everywhere non-negative and integrates to 1, namely if it is a legitimate density function, so will p hat dot be. Furthermore, p hat dot will inherit all the continuity and the differentiability properties of the kernel k dot, so that for example if k dot is Gaussian, then p hat dot will be smooth having all the derivatives. One problem is that the window width is fixed across the entire input space. Various adaptive methods have been proposed to tailor h as a function of the density around x. K nearest neighbor estimator. The nearest neighbor class of estimators adapts the amount of smoothing to the local density of data. The degree of smoothing is controlled by k, the number of neighbors taken into account, which is much smaller than n, the sample size. Let us define a distance between a and b, for example, the absolute values of a minus b, and for each x we define that d1 of x is less than or equals to d2 of x, which is less than or equals to dot dot dot, which is less than or equals to dn of x, to be the distances arranged in ascending order from x to the points in the sample. d1 of x is the distance to the nearest sample, d2 of x is the distance to the next nearest, and so on. If x to t are the data points, then we define d1 of x is the minima of the absolute value of x minus x to the t, where the minima is taken among all possible t, and if I is the index of the closest sample, namely I is equals to argument min t of the absolute value of x minus xt, then d2 of x is equals to the minima for all j which is not equals to I of the absolute values of x minus x to the j, and so forth. The k nearest neighbor KNN density estimate is p hat of x is equals to k divided by 2 times n times dk of x. This is like a naive estimator with h equals to 2 times dk of x. The difference being that instead of fixing h and checking how many samples fall in the bin, we fix k, the number of observations to fall in the bin, and compute the bin size. Where density is high, bins are small, and where density is low, bins are larger. See figure 8.4. the KNN estimator is not continuous. Its derivative has a discontinuity at 1/2 of the value of x to the j plus x to the j plus k, where x to the j are the order statistics of the sample. The Kn is not a probability density function, since it integrates to infinity, not 1. To get a smoother estimate, we can use a kernel function whose effect decreases with increasing distance. P hat of x is equals to 1 over n times dk of x times sigma of t starting from 1 to n of the function of k of the following value, x minus x to the t, then divided by dk of x. This is like a kernel estimator with adaptive smoothing parameter h equals to dk of x, and k dot is typically taken to be the Gaussian kernel.